are live. I can see the very first people joining in. How are you doing, Abhishek?
Doing really good. How about you?
I am well. Excited for this topic of which we have somewhat covered in the past, or we have had some similar webinars in the past of this topic, but none with the examples that we are covering here. So we have some exciting new case examples.
Right.
Isn't that right?
Yes, exactly. I mean, we have a couple of new examples which we haven't shown anywhere in any webinars before, and that's really, uh, yeah, exciting for me. And we have this time we are focusing more on results and what our customers can get most out of our platform instead of a live demo. So that's new, let's say.
Yeah, I think that's a welcome change. Makes it more engaging for the audience. Makes it more maybe perhaps tangible and less sort of nitty gritty. But with that, I see that a decent amount of people have already joined. So let me just kick off the official portion of the webinar. Just put on some introductory slides. So indeed, we are here to talk about MEMS simulation and specifically fully coupled MEMS simulation at scale. Now, just a couple of housekeeping items before going any further. At any time of the event, don't hesitate to ask questions. So if you see something that you find intriguing, you want to ask more, you have this questions tab in the upper right hand corner. At least for me, it's in the upper right hand corner, where you can just submit any questions you have. Now only Abhishek and I see them, so they are not public, and they will sort of remain anonymous. So you can ask freely without any hesitation. Then also we will be handing out some resources, namely the PDF summary of our previous harmonic balance webinar. So we'll be handing out that at some point today in the materials tab. So that will be available there. Now, just quickly, my name is Jukka Knutinen. I work as the head of marketing. I will do this 5 minutes of talking here at the start before letting our star of today, so Dr. Abhishek Desmukh, team lead of our application engineering, get to the actual beef of today. As said, a few minutes of introduction talk here. Then it's Abhishek with the actual content. So going over the limitations with traditional software, some of them, and specifically what kind of the limitations Allsolve is sort of unlocking or eliminating, and then into the case examples themselves and the results and sort of other impactful outcomes of these improved simulation capabilities. Now, yeah, here's just a slide on the handout we'll be handing out. Just very quickly, if there's someone here who is not familiar with Quanscient as a company or as a platform, it's basically a cloud-based FEM multiphysics simulation platform developed by our company Quanscient, a Tampere, Finland-based company developing in 2021. And basically, our core value is natively coupled multiphysics built to scale, which is very relevant to the topic of today. And yeah, trusted in industry, academia, startups, enterprises, everything in between, and some research organizations. I have some slides on some key advantages in MEMS design here, but I thought that it would be best at this point to just pass over the mic to Abhishek to really go over these key advantages through these real world examples and not have me sort of say them with these slides. So I guess with that, I'll stop sharing here and pass the stage on to you. So go ahead, Abhishek.
Thank you, Jukka. And makes sense to look at the examples directly and see for themselves how you can benefit from Quanscient Allsolve. So I hope you can see my slides. Yeah. So I welcome you all on from my side for today's webinar. on fully coupled MEMS simulations at scale with Quanscient Allsolve. Yeah, the agenda for today's webinar is shown here. So we will have a brief overview of Quanscient Allsolve in the beginning. Then we will dive deep into two specific examples in the MEMS community. One of them is MEMS gyroscope, cover some of the important physical effects there. Then the second example, FBARs, so-called film bulk acoustic resonators, and their important effects which should be considered in the simulations. Then some more examples which we have already shown in the previous webinars, but just to highlight what more we can do with Quanscient, and then conclude today's webinar. So it's an established fact that current or today's simulation tools are a bottleneck in engineering. So most or many of the design engineers would like to have more computational capacity. Otherwise, they kind of need to reduce their simulation complexity in some way, that they have to simplify it to be able to run their simulations in their existing capacity. So I have done this in the past. I had to simplify my simulations when I didn't have access to such huge computational capacity. For example, reducing 3D to 2D using some kind of symmetry rules or axisymmetry and so on, or even 1D if I want to run some simulations quickly and I want to run thousands of them, then that's the necessity. On the other hand, engineering decision makers or managers would like to reduce the cost associated, and in that time to I mean, they want to reduce the cost and risk, and at the same time have the impact of simulations on the product. And this can be, let's say, addressed by the several factors. For example, flexible software licensing, which is important to increase the capacity and simulation capabilities of the organization. So yeah, we agree on this. And however, what is now Quanscient doing? I mean, Quanscient is exactly doing, or giving you ability to increase your capacity based on our capacity based model, which essentially transforms transform the simulation from a cost center to a competitive advantage engine. So which actually enables you to run design explorations at massive scale, and in turn resulting into faster innovation cycles. So how we are going to do this? I'll keep it brief. We are doing this by mainly removing limitations in multiphysics. Then we are removing limitations in simulation scalability by providing the infrastructure to run large-scale simulations, algorithms to be able to scale them well, and run large number of such kind of simulations at the same time. And we are also removing the limitations or software licensing. What that means is we are not limiting the number of users, so you can have as many users as you need on same organizational account, and we are providing everything in the same license. So no extra licensing for separate physics modules. We are also removing the hardware limitation, meaning that you have access to the cloud computing capacities as you need, and we can try to, or we can try to address as much as you need based on what we can from the AWS and or even private AWS clouds. And last but not least, which has been also covered in previous webinars, is the installation and IT. So there is no basically maintenance of these compute infrastructure and installation and so on. You have access directly as you get the login credentials. And why exactly is this important? So any any simulation, not just for MEMS, but requires it, or it demands actually the accuracy. I mean, if you want to simulate real world device, you need accurate simulations, and accuracy is enabled by trying to include all, or trying to include most of the effects that make difference, or that affect the device, let's say operation of the device, which can be quite complex. It can be quite multi-scale, and yeah, and you want to do this with minimal approximations as possible. And yeah, and MEMS devices inherently, they are the physical processes underlying the operation, they include quite a lot of variety, including piezoelectric, electromechanical, thermal, fluids, and all these physical processes are kind of acting together, and these needs to be coupled in a consistent way in a finite element framework. And this is what we offer as a multiphysics platform, and this enables us as well to gauge the impact of system level effects, and with the compute infrastructure and the ability to scale the simulations, both in terms of size and the number, you can explore large design spaces. So it's quite important to have this kind of capability if you want to really go close to actual design and model the behavior of device in simulation. So how we do this? So this is our secret sauce, as you might call it. So the domain decomposition method enables us to scale, or to allows us to split the domain into several pieces, and then each of these individual piece of let's say mesh is solved on a new node, or different node, and that way you can parallelize the computation and effectively reduce the run times quite significantly. And yeah, that enables us to scale huge simulations using the cloud computing infrastructure. So having said that, what are the applications that we are active in? So we are currently active and also increasingly growing in the areas of MUTs, or so-called micro machine ultrasound transducers, then ultrasound devices, or then RF filters, micro speakers, micro valves, inertial devices, and we'll see one example today from that, then timing devices, micro mirrors, and so on. So there is large range of applications we can address with Allsolve, and we would be happy to know from you what applications you are running, and what you would like to simulate with Allsolve, and basically solve your challenges in design. And all right, so that was about the Allsolve in general, what we can do and what we offer. Now let's dive into specific examples. So one, or the first example coming up, is the MEMS gyroscope. And we see here, so what's the MEMS gyroscope? So it's a device that senses the angular velocity, which is based on the Coriolis effect. So a typical design is shown here on the right hand side. It has some proof mass, two proof masses, some electrostatic combs which actuate the proof masses via electrostatic drive, and there are some beams which are supporting the proof mass, and then there are anchors which are kind of tiny to see here, but yeah, the whole device sits on some kind of substrate which is not shown in this picture. But in general, these kind of gyroscopes are used in many consumer applications like smartphone or automotive safety, industrial robotics, or precision navigation, and so on. So the design goal of such devices, I mean, there can be many design goals. What I list here are two, or which are potentially two design goals that one can think of, is the maximizing the Coriolis coupling. So what that means is that you try to match the drive and sense mode frequencies so that they are coupled together very well, so that you can your sensitivity of your device is increased by that. And the second goal could be packaging. So packaging environments can have impact on the performance and device, so performance measured by the quality factor. So depending on the requirements and let's say performance metrics, design performance metrics, you can control the these these factors like quality factors and bandwidth. And yeah, these are kind of goals when you want to design the gyroscope. And the question is how Quanscient help in this case. So Quanscient helps in enabling you to run many of these design iterations to optimize basically optimize it in terms of the performance metrics. So depending on what you want to achieve, you can, for example, you can change the proof mass design, or you can change these supporting beam structures, and serve or try to find a design what serves the best for your application. Then we also enable the study of individual effects or physical effects that might affect the performance. So these can be damping mechanisms. So we'll look at few damping mechanisms in today's webinar, what we have done so far. And yeah, understanding these mechanisms can help you understand your device better and then control it in a better way to closely let's say achieve the application that it is intended for. And lastly, you can of course use the 3D simulations, extract the high level parameters like Q factors, which can be then used in your fast or your own ROMs or reduced order models as they call it. And yeah, that can be also one of the utility. Okay, so
Sorry,
this is,
Abhishek, just
yes.
chiming in quickly. Just wanted to remind everyone that, again, if at any point you have any questions, don't hesitate to ask. So let's keep this as an interactive session. And by the way, when it comes to this example, this is kind of a cool one. So I'll let you go back to it. I just wanted to let that know. Thanks.
Yeah, and yeah, please feel free to interrupt, and I'm happy to answer any questions whenever you have one. So yeah, this is the typical design. So now zoomed in, trying to show all the important elements here. So the beam, support beams, anchors, as I said, these are quite tiny, and then edge holes which can actually control the damping and the actual mass of this proof mass in itself. And yeah, in this webinar we will focus on modal analysis, which has been done for the to evaluate the damping effects, and as well as to show how the geometric sweeps can be performed to explore the design space. But that's not the only thing we can do. There is also possibility to employ harmonic balance method to study nonlinear behaviors We will not cover this in today's webinar, but we have a dedicated webinar on harmonic balance. If you are interested, feel free to have a look at it. Yeah, so that's the typical design, and we'll look at the modal analysis or eigenmode analysis in other words, if you're familiar with that. This is the typical mesh that we created with Allsolve or within Allsolve. So one thing what I want to highlight is the layered meshing. So typically in most of the MEMS devices, you have these thin layered structures, and if you think of doing a tetrahedral mesh, it can quite increase the computational requirement, as if you want to resolve the fields in the thickness, then it might need more number of elements. So what we enable with the layered meshing is that you can resolve these fields in reasonable way, while keeping the computational cost to reasonable. Okay, so let's look at some results. So this is these are the two modes that I've found in the modal analysis. These are not the only modes, but I'm showing the two modes that we are interested in. So one of them is on the left shown is the drive mode with frequency about 38 or 39 kilohertz. So this is the in-plane mode or actuating mode, as a or even drive mode, which is actuated by these electrostatic combs. And on the right side is shown the sense mode, which is the out of plane motion. And typically there are let's say capacitive sensing. So there are yeah, electrodes below these proof masses which can sense the capacitance, and then you can sense the motion. So yeah, the point is that you can get these modal modes directly out of the modal analysis, and identify them based on their motion. And what's interesting, or one simulation of this, probably not much interesting, but as I said, to find the right frequency and right combination of frequencies for sense and drive modes, that's what we want to get to. And here I have tried to show one example of, or on the geometric sweeps, where we varied, let's say, h dimension, which is the size of the h holes, for example, and try to see how the frequencies change, or these drive and sense frequencies change with the increasing number of increasing the size of holes, h holes. And understandably, increasing the size would reduce the mass, and as the mass is inversely proportional, or the frequency is inversely proportional to square root of mass, you can expect that the frequency will increase by reducing the mass there. On the other hand, if we try to vary the beam width, for example, you can see that increasing the beam width brings these two frequencies closer in a way. And that there's also reason to that, because this beam is supporting the proof mass, and in plane motion this is affected by the width of the beam. Essentially, the increasing the beam width would increase the stiffness, and that would lead to the increasing the eigen frequency for the drive mode, not so much for the sense mode. And that's why you see there is the slight increase, but still not as much as the one for the drive mode. And this is just to show you an example what's possible with Allsolve. These are two parameters, but not that these are limited to two parameters. You can parameterize your geometry as much detail as possible, and try to run these designs. And the key thing is to identify what you want out of the simulations, and what which parameters would be the most interesting ones. So yeah, this is something to keep in mind. Okay, so that was about enabling large scale simulations. Now let's look at some of the physical effects that are important for the MEMS gyroscope. And there are several damping mechanisms that might come into play. So in real world, your gyroscope is not, let's say, isolated from the environment. So the anchors are, let's say, it's sitting on a substrate. Through the anchors it's losing the energy, or some of the energy is transferred from the anchors to the substrate, and that's what we call the anchor losses. And if it's sitting in some kind of packaging environment, either vacuum, or if there is some non-vacuum packaging at some low pressure, there is still effects such as so-called squeeze film damping. So the effect of these, let's say, gas around, or gas film around the gyroscope, that will affect, yeah, the or that will damp out the yeah, the motion of the gyroscope. So let's look at results on the anchor losses first. And always, as always, I'm showing two modes here, drive mode and sense mode. As in the animation, you can see the in plane motion, and for the sense mode, out of plane motion. And I have also written here, or collected here, the Q factors or quality factors, which are readily obtained from the eigenmode analysis. You can see that in the drive mode, there is the value is quite high, as it's probably not losing. So the Q factor is essentially the energy stored divided by energy lost to the environment via whatever mechanism, and here through the anchors. So in the drive mode, it's not losing much energy, so the quality factor is high. In sense mode, it's losing more energy because of this motion, out of plane motion, and you see 2 orders of magnitude reduction in quality factor. So these can be quite important metrics that you can get out of the simulations readily. When we look at the squeeze film damping, again, two modes here shown side by side. And as you can see, the fluid, or the gas film, has a significant impact. The Q factor has now reduced by a lot here, even in the drive mode, and the sense mode is also reduced by 2 orders of magnitude. And what I want to highlight here, these are now simulated individually, so they are not interacting with each other. So once with only anchor losses, these are the simulations only with the squeeze film damping, so that you can study the impact of each mechanism individually, and try to extract important parameters from these simulations. We can go a further step in the squeeze film damping to study the impact of different factors. So here, for example, I wanted to look at the effect of, so the squeeze film damping also, I mean, it essentially models the effect of viscosity, and then the hydrodynamic forces on the gyroscope. And as you can see, increasing eigenfrequencies, with increasing eigenfrequency, your Q factor is increasing. What that means is that these effects become less important, so you lose less energy at higher frequency compared to the lower ones at the same, or in the same kind of environment. So these kind of effects can be studied individually. Then you can also, or what we did in this case was vary the ambient pressure to study the impact on bandwidth in addition to Q factor. So the bandwidth and Q factor go together. So when the Q factor increases, bandwidth is decreasing, which is quite understandable. And what we see, or what we can use this information for, is you can find the right kind of environment for your requirement. So if you want a specific quality factor and specific bandwidth, you can try to package it in certain environment, so that you can meet this is design criteria. Then The third damping mechanism is thermoelastic. So while you are I mean, these are the effects uh, happening through the elastic deformation that then converts into thermal energy, and then yeah, you lose the energy via this thermoelastic mechanism. And what I wanted to check was how the effect of the thermal expansion, so the coefficient of thermal expansion, is affecting the performance. And I found this nice plot online in this publication, where they have measured the coefficient of thermal expansion of silicon. And interesting thing is that it also goes negative at negative temperatures. So you might wonder now, what in what kind of environment you might have these kind of temperatures. So I could think of one application, for example, low Earth orbit. So satellites in low Earth orbit, they might encounter such environments, such extreme environments, ranging from negative temperatures like -65 to even like 120 degrees, depending on which side of yeah, where they are located in space between sun and earth. And you can see that the effect is quite significant. Just note that the axis is logarithmic, and you can see that there is orders of magnitude difference if you just change temperature by maybe few degrees. And it can also go, because of this negative heat or the negative coefficient of thermal expansion, it can also change in on the other way around. And this is what I found really interesting. And yeah, these kind of individual effects can be obtained from Quanscient Allsolve. Now, in real world, these three damping mechanisms cannot be isolated, so they coexist together. And what happens if we want to study the impact of these three together? So this is exactly what I did here, included all three damping mechanisms, trying to calculate the quality factor and yeah, and the frequencies for these with these mechanisms. And this was uh, done in a full 3D, 2.4 million DOFs, used about 64 cores, and took just 10 minutes of runtime to obtain 5 modes, which include these two modes of interest for us. And yeah, that was quite interesting to see. What I want to come back, or what I want to highlight in this case, is how each of these mechanism is acting, or what are the contributions of these mechanisms. So this is what I wanted to study, and this is what I shown here. So for each of these modes, drive and sense modes, I plotted the percentage contribution of these different damping mechanisms. And for pressure of 100 pascals, it seems that the squeeze film damping is dominating. So it's the largest effect on the quality factor is coming from the squeeze film damping. Other dominant, or the next one, is the thermoelastic damping, and the anchor losses are negligible. They might not be visible here in drive mode, although they are slightly visible in sense mode. And yeah, interesting thing I wanted to check again, or further check, was in the literature I found this inverse contribution formula. So people, or the engineers, do this effective calculation of effective Q factor based on individual one. This is the inverse formula that's commonly used. And I wanted to see if I now do this fully coupled simulation, and is that formula still valid. And what I found interestingly was that it might not be necessarily. So what you see here is the blue bars are the calculations of the inverse formula, and the red ones are from the fully coupled Allsolve simulation, including all three mechanisms. What I see here is that the drive mode Q factor is almost reduced by half, and on the other hand, the sense mode Q factor is increasing. This was a bit confusing for me, but when I thought, I gave it a thought and tried to understand what might be happening. So one thing I came to understand was maybe the squeeze film damping is kind of acting in compensating or acting and compensating the effect, the anchor loss effects and thermoelastic damping. So these, there can be interactions between these damping mechanisms which might compensate or amplify each other, and this will have an impact, and this is what is visible. So you might end up with slightly or lower values of total Q factor, whereas full in reality it might actually be slightly higher or even higher, depending on the materials and environment and so on. Okay, so that was about the gyroscopes. Again, feel free to ask questions in between if you have ones, but if we don't, then.
There was indeed just one question,
Okay.
just asking, do you have an example of coupled simulation including structural mechanics and electrostatics?
Structural mechanics, and yeah, there are definitely examples. One of the examples I can think of is easily the CMUTs, which include structural mechanics for the membrane, elastic membrane motion, and then the CMUTs are driven by electrostatics. And but again, depends on what applications you are looking at, but we definitely have examples including those.
All right. And I don't know if we said it already, but we indeed have reserved some time at the end for a Q&A session, so we can get into deeper questions also there. And of course, anyone can also always follow up at any point after the webinar by email, LinkedIn message, anything like that. But okay, let's keep the show going.
Right. So the next example is the FBARs. So these are kind of RF filters. So let's look at what that, if you are new to this, and like I was new to this. So these FBARs are essentially parallel plate capacitors, and in between these parallel plates is a piezoelectric material sandwiched as a dielectric, and when you apply the voltage or the potential across this piezoelectric material, it resonates with a frequency, certain frequency, which is equal to the half of the acoustic wavelength. So in a way that when the wavelength of the, let's say, the elastic material or the is the equals the thickness of the film of the material, then you will get resonance at this. And these filters are mostly used in high frequency RF applications, and one app or most applications could be in mobiles or wireless communication. Think of the 5G or 6G communication channels. And yeah, these are basically used to filter out the frequencies in particular band. As an example, what I have shown on the right hand side, you see here uh, really the transmit and receive bands here, where you can actually have these quite narrow band structure, and have limit their, let's say, range of frequencies, so that you have crisp signal and sharp signals there. And design for such kind of device, design goals, again, we need high quality factors so that we don't have a lot of smearing, then high selectivity, and we want to reduce the lateral modes of propagation, which we'll see how they affect the performance in a way. And yeah, these are the design goals, and how Quanscient helps again in this case is the fully coupled simulations. And this is actually one of the examples that we just had a question about. So we have here structural mechanics or mechanical wave, and including the electrostatics, which is now yeah, also includes the piezoelectric materials and properties. So all of this physics fully coupled together, and again the Quanscient helps to run these simulations at massive scale. And these devices are, because they are operating at high frequencies, they're uh, the meshes can be quite dense, and you need really the large computational power to be able to simulate these in 3D. And 3D is important because we'll see that the lateral modes are or can be identified only in 3D simulations. And once, yeah, why we want to identify those, because once you know where what you can expect in terms of lateral modes, you can try to mitigate them by changing the shape or any other parameters that can help there. All right, so that's the overview, and then I want to take this as an example. So this is really simplest example here. So all square domains, we have aluminum nitride as the piezoelectric material between the two electrodes here, and it's sitting on the silicon substrate. We have some absorbing boundary conditions which let the waves, so to avoid the reflections, which um, yeah, which might come back from there and affect the performance. And the series frequency, as we'll see, is 2.67 gigahertz about. This is the typical mesh. In this case, we have used full tetrahedral mesh, but that's not, and we can of course also could have done this with the layered meshing. Yeah, then coming to the results of this design. So what I've plotted here is the impedance magnitude over frequency, and on the right hand side plot, or right hand axis, I have plotted the phase. So the phase is the green plot, and the impedance is the blue plot. And you can see that there are two distinct peaks here. One is the series, one is so-called series resonance, and the other on the right side is the parallel resonance. You see that series resonance offers the least impedance. On the other hand, parallel offers the highest impedance, and in between these two resonance peaks is lies the let's say the band where the frequencies, or the filter lets the signals pass in this band of frequency. And this can be thought of in a circuit analogy. So the series resonance kind of offers the free path um, to the signal, and parallel resonance is kind of essentially acts as an open circuit. So, and in between there is a close match of impedances, and that offers the maximum power transfer between these two peaks. And that's why you get this yeah, sharp or stable band, and then sharp drop at the end of this. And what I wanted to highlight here was these impedance plots show these ripples here, or so-called other modes here. And these are the lateral modes, which are not desirable because they are of course affecting the impedance itself, and try or adding the noise to the frequency. And any noise that's added to the signal is undesirable. And here are some of those shown. So the first left top mode is the one for the series resonance, which is close to what we designed for, 2.67 gigahertz. And the other modes that are shown, these are the lateral modes, or these are the undesirable ones that are here acting as a, let's say, making more noise into the signal. So this simple design is probably not the best one if you are designing RF filter. and among you might be an RF filter expert who can immediately see that already. So we wanted to check what would be, what can help to mitigate this, and for that we imported a real let's say FBAR design. So I wanted to spend uh, a bit of time on how we do that. So we imported this geometry from softmems, where we have developed this API based workflow together with softmems, which lets us import the design or the parameterized geometries from softmems into Allsolve. And the the good thing is that you can design your process in softmems and have everything there and readily export that to Allsolve. And it avoids some of the issues like true curves, in which, in for example in GDS these cannot be preserved, but we avoid such issues by directly importing these geometries from softmems. And we have also implemented automated setup, which lets us or which speeds up the setup of the simulation based on the definitions in your softmems design. And the whole workflow can be driven by a Python script, and this lets you run thousands of designs, which are generated at the design level and which are fully manufacturing, including manufacturing details and so on. You can use it for design of experiments, optimization, or whatever study you want to do. Okay, so we imported this real design, and we I think this was a bit optimized to reduce the lateral modes. I ran the impedance sweep or frequency sweep, extracted the impedance plot, and you can see indeed some of the modes are damped, or they are gone uh, from the characteristic. There are still some of the modes remaining. Let's look at the series mode, and this is the parallel mode. I wanted to also see what are these, and here you can see there is some kind of intermediate lateral mode here, and also the other one here. So ideally we would also like to get rid of those. This is essentially a shape optimization problem, where you can design your shape of these electrodes and the yeah, essentially the package itself, so that you can get rid of unwanted frequency modes and keep the ones to get the best, let's say, band of or best filter out there. Okay, so that concludes the FBARs, and yeah, so there are more MEMS examples that we have covered in the past, which I wanted to show a few of them. So electrostatic microspeaker, which we have shown before. Then PMUTs, we have covered this in very detail in the past. We can do large arrays as shown here, can extract all kinds of outputs, beam patterns, far field beam patterns in different configurations. Then CMUTs, also crosstalk can be extracted from crosstalk patterns can be extracted. And lastly, variable RF. So this was quite new. This hasn't been shown before. I wanted to briefly show how the effect of mechanical bending of, let's say, a coplanar waveguide, and how that affects these scattering parameters in frequency domain. That's what's shown here. And at the same time, you can also, let's say, account for the effects, the warpage effects or mechanical effects on these. So I hope that this will be covered in future webinars sometime. So I wanted to end this webinar at this point. To conclude, we showed how Quanscient can help you to perform fully coupled simulations, and that too at massive scale, allowing geometric sweeps, including different damping mechanisms or damping effects, and also capturing 3D effects wherever they are important, especially in FBARs. And yeah, that would be the end of webinar from my side.
All right, so now there's still a couple of things to go through just quickly, but next up is basically the Q&A section. So let's just quickly address this one question that was already there. I think this was, if I'm not fully mistaken, was related a like kind of technical specific question for the gyroscope example, asking that could it be that the simulation has been done only until 10,000 Pascal and not to ambient pressure? And it was clarified to be 101,300 Pascal.
Actually, yeah, in this case, I chose the range between these, but I mean, I have done simulations at ambient pressures as well, but it's just not plotted here. Yeah. Actually, that was the first simulation which I did before we took into account these environmental effects, because they need special treatment for the rarefied environments, where the viscosities, when it enters into molecular regime, we cannot account for, or I mean, we cannot model this as a continuum approximation, and there we still, if we want to use this approach, we have to modify the viscosities with some specific models, and this is what we did. But we started first with ambient pressures and then went on building or adding more effects there.
All right, thanks for the answer. Now, Abhishek, you mentioned the harmonic balance feature. Just to let everyone know, as promised in the start, I have now added this harmonic balance white paper into the materials tab up in the right-hand corner. So it covers at least a few examples of what the harmonic balance is and how it is applied in Allsolve, what kind of benefits it provides. Could you just quickly, Abhishek, cover the key things? Just what is the harmonic balance method? What does it enable our users to do?
Yeah, the harmonic balance method is essentially frequency domain analysis, but for nonlinear effects. So you can essentially simulate nonlinear processes. For example, if you want to include the effect of, let's say, fluid flow, which we have shown for the microspeaker in the previous webinars. Let me come back to that. So for example, here, so we have included here all of these electrostatic, solid mechanics, and fluid dynamics, which fluid dynamics out of which is essentially nonlinear. And what that does is that you can have, let's say, some components which are, even if you are driving at certain frequency, the effects can appear at higher modes or multiples of this fundamental frequency, and these can be captured without running a transient simulation, which you might have to run for thousands of cycles. But harmonic balance method lets you do once, let's say, and get all of this information directly in the frequency domain. And the good thing is that you don't need to simulate all the harmonics sequentially. You can pick which harmonic you expect, which higher harmonics you expect based on fundamental frequency, underlying physics, and then only try to get that. And this is something unique that we have as a feature.
All right. And yeah, as said, that full white paper is in the material tab. At this point, let me just quickly fire this poll here. So just if what you saw here today is of interest to you and you would like to explore, or just have a chat with us to basically explore, well, what could these features and this platform, how could it help with your specific problems? What essentially just to cover what could it do for you. So if you're up for a conversation like this, just at some point after the live event, you can just answer it in this poll. And this poll again is completely anonymous, so no one will see what you answer here except for us. And then someone from our end will reach out sometime after the live event. I'll let this be here on for a second, but in the meantime, we still have a handful of minutes left. So if anyone has any burning questions or even non-burning questions, just questions whatsoever, we're here still for a few minutes to answer them live. But as said, at any point during after the event, if a question emerges, you can reach out to us through our website. You can reach to either myself or Abhishek. I assume directly on LinkedIn, if that is, Abhishek, fine with you, or by email or by any other means. So we're always here available.
Yeah, anytime.
All right.
Feel free to connect with us on LinkedIn, and yeah, we are happy to answer your question or yeah, understand more about your applications and how we can help you.
Closing the poll now. Thanks for all the responses. Let's just give a minute or two for any questions. Looks like we were quite nicely on time. Just to let everyone here know, if you haven't already, or if you aren't following us on LinkedIn at Quanscient, I would strongly recommend you do that. I would actually say right here something that we haven't yet said elsewhere. This is kind of an exclusive thing, is that we are releasing something very exciting and very interesting in a few weeks' time, within 4 weeks or so. Can't unfortunately go into what exactly, but rest assured, it is fascinating stuff, and we'll be releasing that in, as I said, in about 3-4 weeks, making a lot of noise about it on our company page, so Quanscient on LinkedIn, and in our newsletter, Quanscient Weekly as well. Once again, that's the kind of thing that you really don't want to miss. So if you aren't already following us on LinkedIn, highly recommend you do so. I still think we have time for one more question, which got right here. So there was a question: how to solve problems including quantum computing, like optimization of DC-DC converter parameters. Anything you can say on that, Abhishek?
I honestly, I mean, that's a new topic for me in itself, but if what I can comment on is what we can do is we have this multi-physics framework where you can apply any physics, including electrostatics or current flow or anything that you need for that kind of application. And I'm sure we can get in touch with you and try to understand what exactly you need, and get in, let's say, yeah, get you the right person who is expert in those kind of simulations, so that you can get most out of this. But yeah, that's the only thing I can say at this point. I'm really sorry if I haven't answered your question correct way, but yeah, do get in touch with us, and we will help you from there.
All right, indeed. Well, that's all the time we had for today. Once again, big thank you for everyone who joined here, and thank you, Abhishek, for your wonderful presentation.
Yeah. Thanks everyone for joining.
And see you in the next one. Bye bye.
See you. Bye.